So far, our story of the growth and development of the universe has included relatively familiar things: stars, galaxies, gas. And even though dark matter isn't exactly familiar, perhaps you're beginning to get a feel for it. But this lecture, I want to introduce a very different kind of character. If this was a traditional creation story, I'd be introducing a dragon or a demon or some ungodly, destructive power. But in the real universe, this ungodly power takes the form of massive black holes. At the heart of essentially every galaxy lies between 1 million and 1 billion suns of matter, crushed into a region smaller than the solar system, whose powerful gravitational field causes essentially everything within its vicinity to zoom around at almost light speed. It really does evoke the idea of a fire-breathing dragon hiding in its lair. So in this lecture, I want to tell you some of the story of these massive black holes and how they play a role in affecting the lives of galaxies. So let's begin with the amazing observational progress in finding massive black holes at the centers of galaxies. The subject took a huge step forward in 1997 when the Hubble Space Telescope had a spectrograph installed that allowed astronomers to measure, using Doppler shifts, the movement of stars and gas very close to galaxy nuclei. Here's an example. Hubble zeroes in on the center of this elliptical galaxy in the Virgo cluster and then places the tiny spectrograph aperture across the nucleus. At each point along the aperture, a spectrum is made which shows the Doppler shift of the orbiting gas and stars. In this case, within just 25 light years of the nucleus, the gas is orbiting at over 400 kilometers per second. You can see also the drop in rotation speed away from the nucleus, just like for the solar system, showing that the gravity comes from a single mass at the center. Applying Newton's laws, just as we did in Lecture 9, you can measure a mass of 300 million solar masses, far more than is present in the actual stars. Now, since then, similar observations have been made for nearly 100 galaxies, and in essentially every case, the Doppler shifts indicate a massive object right at the center. Even our own Milky Way galaxy has a central black hole. Here's a beautiful nighttime view of the Milky Way, with its center located right here in the constellation of Sagittarius, smack behind a lot of obscuring dust. Now, fortunately, if we look using infrared light, like this image, you can see through the dust. Zooming in, you see a central star cluster, and two groups, one in Germany and one in the United States, have carefully followed the motion of the stars in this cluster. Here's a movie in which 15 years pass in 5 seconds, and you can see nice, neat elliptical orbits around a central point. Here it is repeating. Try to watch star 14 carefully. At closest approach, star 14 is moving at 3,000 miles per second and comes within 6 light hours of the central point. That's as close as the planet Uranus is from the Sun. Analyzing the orbits carefully essentially proves that sitting at the central point is a black hole with 3.7 million times more mass than the Sun. Now, as I said, for almost 100 galaxies, black holes have now been found and their masses measured. And there are two remarkable facts that have emerged. First, essentially every galaxy that's been looked at has revealed the presence of a black hole. The only exceptions are galaxies with no real nucleus or bulge, things like our local dwarf galaxies, the Large and Small Magellanic Clouds. Otherwise, massive nuclear black holes are a normal galaxy component, a part of its anatomy, like an arm or a leg. And secondly, as this graph shows, the black hole mass up the y-axis increases with the galaxy bulge mass. That's along the x-axis. For example, the huge galaxy M87 has a 3 billion solar mass black hole, while, shown at the same scale, the lightweight galaxy M32 has a lightweight 2 million solar mass black hole. And on average, the black hole mass is about 1/1000th of the mass of the galaxy bulge. Now, at this point, I should say something about the nature of black holes. From our perspective in this course, their main quality is simply that they contain a great deal of mass within a tiny size, so that close to the black hole, the gravity is extremely strong. Just to give you an idea, here's the Earth with about 10 to the 25 kilograms of rock within a sphere 8,000 miles across. So near its surface, gravity pulls with modest force. We have little arrows. But if I drop a bag of flour through 1 foot, the energy it releases sounds like a thud. Not very much gravitational energy released there. But if I crush the Earth down to make a black hole, it's now 1/2 inch across, with the same mass, 10 to the 25 kilograms. So the gravitational force nearby is huge. We have huge arrows. Now, drop a bag of flour from 1 foot. It falls in about a nanosecond, moving at almost the speed of light, and the thud of its landing is equivalent to detonating a large hydrogen bomb. In fact, the gravitational energy that gets released when matter falls into a black hole is roughly given by Einstein's famous E equals mc squared. So black holes are potentially incredible sources of energy. Feed them anything, and you can convert the infalling mass almost directly into energy. Now, in practice, the efficiency isn't quite 100%, it's more like 10%. But even so, that's enormously more efficient than, for example, nuclear energy at 0.1% or chemical energy at 1/1,000,000% efficiency. Now back to the astrophysical context. A galaxy nucleus with a black hole weighing, let's say, 50 million solar masses. At that mass, its size is about the size of the Earth's orbit. This is tiny relative to the galaxy. From our scale model in Lecture 2, it's a pinhead in the middle of the United States. Around this pinhead, stars are the size of human cells 10 yards away, where the black hole's gravity is much weaker. So for most of the time, the black hole just sits there and is, well, it's black. You don't see it. This is the condition of the black holes I just showed you in that elliptical galaxy and in the Milky Way. It's all but invisible, although its gravity affects the orbits of stars out to a few light years, and that, of course, is how we know it's there. There is another situation that can occur. If gas can fall into the very center, close to the black hole, then it settles into what is called an accretion disk. It gradually spirals inwards, orbiting faster and faster as it gets closer and closer to the black hole, until it's basically moving at light speed just before it falls in. As the gas moves through this disk, before it finally enters the hole, it can release huge amounts of energy, and the galaxy nucleus lights up like a beacon. Astronomers call this an active galaxy. It's a galaxy whose central black hole is having a meal. It's devouring gas and stars and releasing energy as it does so. Now, exactly how this accretion disk behaves isn't, in fact, understood very well, but we think that there are 3 primary ways that energy is released. First, the hot disk is extremely bright. It produces photons, from infrared to X-rays. Secondly, a wind blows off the disk. And third, 2 fast-moving jets of very thin but very hot gas are launched perpendicular to the disk. Let's have a quick look at some active galaxies. They go by various names: quasars, Seyfert galaxies, radio galaxies, depending on just how the energy makes itself known and how much energy there is. Here, for example, are some quasars. Their active nucleus is so bright one can barely see the host galaxy. This tiny region, smaller than the solar system, is producing more light than all 100 billion stars in the galaxy combined. Here are some active galaxies whose black holes are driving out powerful jets. These jets produce radio emission, which the images show as red, while the visible light from the galaxy of stars is in blue. So you can see how the jets push way out, well beyond the galaxy, out into the galaxy's halo. Not surprisingly, these are called radio galaxies. Now, you may have noticed something interesting, particularly about the quasar images. They seem to be in disturbed or interacting galaxies, and this gives us a clue about what triggers activity, what initiates feeding the central black hole. Remember from last lecture, when galaxies interact, some of their gas falls to their center. Here's a movie of two galaxies colliding to remind us, starting with just the stars and dark matter. Now here's the same collision, but showing just the gas component. Notice how it ends up in a much more compact region than the stars. And here, let's watch that last part again, zoomed in a bit. The two gas disks merge, and as they do so, the gas really settles to the center. So these simulations show how lunch gets transported down to feed the central black hole, and so the galaxy becomes active. Now let's begin to put all of this into a cosmological perspective. In previous lectures, we've seen how galaxy interactions were much more common in the past, and that in turn led to much higher star birth rates in the past. Well, since feeding black holes also seems to be triggered by galaxy interactions, do we find evidence that activity in galaxies was also greater in the past? And the answer is a very definite yes. Here's the distribution of 10,000 quasars, very powerful active galaxies, in one of those pie diagrams where we are at the center. Look at the distribution. There are virtually no quasars nearby, whilst there are thousands at greater distances. Now look at the time axis. We go right out to 14 billion light years, essentially all of cosmic history. Clearly, quasars were much more common in the past compared to today. Here's the final analysis that shows the rise and fall of black hole feeding. There is a rapid turn-on after about 1 billion years and a heyday between 2 and 3 billion years when powerful quasars were 10,000 times more common than they are today. Since then, quasar activity has gradually shut down as galaxies have settled into a more sedate and tranquil middle age, starving their central black holes. But just occasionally, in today's universe, galaxy interactions send a bit of gas down, a snack, for the dormant black hole, and the activity resumes once more, but at a more modest level. We call these lower power active galaxies Seyfert galaxies, after the American astronomer Carl Seyfert, who first studied them in the 1940s. Now, unlike humans, when black holes eat, they don't excrete. This is a one-way trip for the food. So all this discussion of feeding is equivalently a discussion of their growth, of their acquisition of mass. After all, how do you think a black hole weighing 1 billion solar masses actually got there? Well, maybe you feed an initially small black hole at a rate of 1 solar mass per year for 1 billion years. Let's just check to make sure this is reasonable. 1 solar mass per year is equivalent to about 1 Earth mass every 2 minutes. Now, if you convert that mass to energy, E equals mc squared, at 10% efficiency, you get 10 to the 39 watts of power. That's about 1,000 billion times the power of the Sun, or 100 times brighter than the Milky Way galaxy. Yes, that's about how bright quasars shine. But that's just their growth. How do you get those initial seed black holes, which then feed and grow? Well, at the present time, we don't know for sure. Maybe they formed when the first stars formed, or maybe later, when the first galaxies were assembled. But either way, it must have been fairly rapid, because the most distant quasars were shining brightly just 1 billion years after the Big Bang. Now, at this point, I want to broaden our discussion of black holes. So far, I've talked about them because they're a part of almost every galaxy, and they're interesting in their own right. But let's not lose sight of our overall story here. We're trying to explain how the population of galaxies came to be the way it is. And so far, we've really only considered one main plot line: galaxies developed by gravitational interaction and hierarchical merging. But in the last 10 years, we've begun to recognize that this cannot be the whole story. There is a second plot line, and it goes by the rather prosaic term feedback. Basically, the huge energy release from galaxy centers, due either to black holes or high star birth rates, can severely affect the galaxy and its environment. And in some circumstances, it can shut down star formation and inhibit the further construction and growth of galaxies. Returning to our dragon metaphor for a moment, despite being confined to its lair, the dragon's fiery breath scorches the surrounding land, preventing anything from growing. So let's now locate this new theme of feedback in its broader context of galaxy growth. And to do that, we need to consider what's called the mass distribution of galaxies. Now here, for example, is a sketch of the mass distribution of humans. It has a peak around 200 pounds, a short tail above for obese adults, and a longer tail below for children and infants. It gives a pretty good feel for the human body. We're way bigger than mice or ants, and we're smaller than elephants or whales. So, what do you think is the equivalent graph for galaxies? Where I'm meaning the stars now, not the dark matter. Is there a maximum or a minimum galaxy mass? And if so, why? Now, I'm going to keep you in suspense because I want to first show you a very plausible guess. Remember that hierarchical merging builds a whole population of dark matter halos, into which atomic matter falls and makes stars. So maybe each dark matter halo contains a galaxy. So we would expect a galaxy mass distribution to be the same as the halo mass distribution, but perhaps shifted a bit because there's about 6 times less atomic matter than dark matter. So with this idea, we need to know the mass distribution of dark matter halos. Now, currently, we can't measure that observationally, but we think computer simulations are sufficiently trustworthy to provide the answer. Now, I'll be discussing these huge cosmological simulations next lecture, but for now, let's just go straight to the results. So here's what they calculate for a typical distribution of dark matter across a huge region spanning hundreds of millions of light years, containing hundreds of thousands of dark matter halos. As you can see, there are relatively few big halos, more medium-sized halos, and lots of little halos. And when you count them all up, you get this graph: the mass distribution of dark matter halos. Notice the axes are exponential and go from huge galaxy cluster-sized halos of 1,000,000 billion solar masses right down to tiny dwarf galaxy halos of just 1 billion solar masses. As is so often the case in astronomy, there are way more small things than big things, and above some threshold, nothing bigger is found. Now, allowing for atomic matter being 6 times lighter than dark matter, we might expect a galaxy mass distribution like this. So what's the real observed galaxy mass distribution? Are you ready? Here it is. Well, the good news, I suppose, is that they do match for Milky Way-sized galaxies, and the overall shape is similar. Many more small galaxies than big ones, with a steep drop in the number of big galaxies. But the bad news is that the really big halos simply don't contain really big galaxies, and there are far fewer dwarf galaxies than expected. So we're beginning to get the picture here. To make galaxies, two things must happen. First, you must make the dark matter halos. That's okay, we understand that. But then you need the atomic gas to settle into those halos and form stars. And that step isn't straightforward. It's vulnerable to several processes that can inhibit it. Now, the reason galaxy formation is suppressed has all to do with the depth of the gravitational field of the dark matter halo, how strongly it pulls on the atomic matter. Here's a sketch illustrating the pull by the size of a valley into which the gas is falling. For the biggest halos, the energy of falling in heats the gas so much that it can't cool to form stars. These enormous-sized halos make clusters of galaxies. Remember from Lecture 9, though, these also have huge hot X-ray emitting atmospheres. There's plenty of atomic gas, it's just way too hot to form a huge galaxy. Of course, pre-formed galaxies do fall into the halo, and we have the familiar galaxy cluster, the Coma cluster in this example. Now, in slightly smaller halos, where the gas could cool, energy coming out from big black holes in active galaxies is thought to keep the gas hot, so once again it can't cool to form stars. Here's an example of a galaxy with an X-ray atmosphere, shown in blue, and a black hole-driven jet, shown in red. Notice how the jet has pushed two big holes in the atmosphere, which heats it and prevents it from cooling. In even smaller halos, the problem is holding on to the gas. Gravity is so weak that when the first stars and supernovae form, they blow the gas back out, and this halts the formation of a small galaxy. Actually, we see this sort of thing happening nearby with starburst galaxies. Here's a lovely image of the nearby galaxy M82. It has loads of star formation and supernovae, and you can see how they're blowing out the gas in these great plumes above and below the galaxy. Now finally, for the smallest halos, the gravity is so weak it can't even pull in the gas, because the gas has pressure, and this prevents it falling in, just as the air in this room doesn't fall towards the weak gravity of my body. So let's now see what happens when we fold all of these mechanisms into our understanding of galaxy formation. Now, as you might imagine, these four mechanisms are complex, messy things. We're barely able to model them for a single galaxy, let alone a million galaxies in a giant cosmological simulation. So to make progress, these processes are inserted into the giant simulations using a shortcut method, and the resulting hybrid is called a semi-analytic model. Basically, the giant simulation is run for the dark matter, but the complex gas processes are added using simple formulae that describe things like the fraction of gas-forming stars, or the efficiency with which supernovae blow the gas out, and so on. In all, there are about 10 such formulae. So let's look now at the population of galaxies that emerge from these semi-analytic models. Here you can see in grey the dark matter distribution, what provides the framework within which galaxies might form. Now the coloured dots are where the galaxies are forming. Here, at just 2 billion years after the Big Bang, they're mainly blue, which signifies they have high star birth rates, so many young stars are present. Let's come forward in time. More galaxies form, and in many, the gas is blown out, so star birth ceases, so the population of stars age. And that aging population is color-coded, green, orange, and red for the oldest population. And by today, we have a population of galaxies with lower overall star birth rates, they're more yellow and red, and the red galaxies, these will be the ellipticals, are found in the densest regions. So the model certainly seems to match two key results from previous lectures: the decrease in overall star birth rate and the tendency of galaxies in dense regions to be ellipticals. Now, what about the galaxy mass distribution? Well, here's our previous graph of the halo mass distribution in red and the observed galaxy mass distribution in blue. And here are the results of the semi-analytic model in green. Now, that's an impressive match, although it isn't quite as impressive as you might think, because, don't forget, some of the model's free parameters were chosen to optimize the match. But even so, I was impressed when I first saw this. There are other things these models get correct. They get the history of star formation and quasar activity roughly right, early wild times, followed by a steady decline. They also get the correlation between bulge mass and black hole mass correct, because the same conditions that build bulges also feed black holes and cause them to grow. Well, I think at this point you've got the picture. We're beginning to explain, in broad terms, quite a range of key galaxy properties. It's still early days in this subject area, and in the coming years you can expect to see significant developments, both in the observational story and its parallel, the theoretical and computational story. We've covered a lot in this lecture, so let me quickly summarize the main points. Since the installation of the spectrograph on Hubble, we now realize that essentially all galaxies with a bulge also have a massive black hole. In today's universe, most of these black holes are invisible, except for their influence on the motion of stars and gas nearby in the nucleus. However, if gas falls into the black hole, the enormous drop liberates approximately 1/10 of the mass of infalling material as energy, and we say the galaxy is active. Of course, galaxy interactions cause this feeding of gas to the center, so not surprisingly, we find activity to be more common in the universe's past when interactions were common. The enormous energy coming from galaxy nuclei can significantly influence subsequent galaxy formation, a process known generally as feedback. One way to uncover the effects of feedback is to compare the mass distribution of dark matter halos with the measured mass distribution of real galaxies. And when you do this, it's clear that something is preventing the really huge and really small galaxies from forming. We think truly giant galaxies can't form in part because the gas in huge halos is too hot and thin to cool and settle, and in part because jets driven by black holes keep the gas hot and prevent it from cooling. And we think tiny dwarf galaxies can't form in part because supernova explosions drive the gas out of the galaxy before it can properly form. When all these effects are included in the giant cosmological simulations, many of the observed properties of galaxies are found. And although it's still early days in this particular subject area, it seems we're well on the way to understanding, at least in broad outline, how the population of galaxies has come to be the way it is. But these are all still only the internal properties of galaxies. We have one final and critical aspect to look at, and that is the location of the galaxies, how they fill the universe, the patterns that they form. And that's the topic for our next lecture.